All right, good evening. We are going to move on to Chapter 7, talking about the central limit theorem today. Let me get my laser pointer. There we go. All right, this is where things start getting a little bit more complicated. Um, so we're going to talk about the central limit theorem, and to do that, we're going to talk a little bit about sampling distributions. So the book definition is it's a distribution of sample statistics for samples of a given size. Uh, so if you're like me, you look at that and go, huh? It's not a very clear definition. The examples later on will make it a little bit more clear, but basically, a sampling distribution is the distribution of the consisting of the descriptive statistics of various samples. So if I take a population of, let's say residents of Marietta, I don't know how large Marietta is offhand. Let's call it uh, let's call it 20,000. Um, Reasonable, probably. Might be probably a little more, but let's assume Marietta is 20,000 people. Um, so a sampling distribution would consist of the results for subgroups of that. So if we took a sample size, let's say we our sample size was 500 people, and we compiled results for 500 people and the next 500 people until we had all 20,000 people accounted for. The the distribution made up of those results would be our sampling distribution. More specifically, we'll talk about the sampling distribution of sample means. So in our example of Marietta, we've got our groups of 500 people we sampled. The average result, whatever it is for each group, would be, of course, the mean for that sample. If we collect all the means for all those samples, then we've got a distribution of means, of sample means. And that's our sampling distribution of sample means. Okay. Um, and yes, it is easy to get lost in all that sampling, or all that use of the word sampling. It's okay. Um, it's it is some confusing terminology, and it is okay for it to be confusing. Um, it's a lot simpler in use than it is in um, description, and hopefully the examples will make that clear. Okay, so let's talk about the central limit theorem. If we have a population with some mean and some standard deviation, a sampling distribution of sample means has three characteristics. Um, if if either the sample size is at least 30 or the population is already normally distributed. Okay, first off, the mean of the sampling distribution of sample means, which we're going to call mu sub x bar, uh, mu being the Greek letter there, subscript x bar. Mu sub x bar, the sampling distribution, the mean of the sampling distribution of sample means, is going to be equal to the population mean. Again, if the sample size is at least 30 or the population is normally distributed. Standard deviation then, sigma sub sigma sub x bar, is the population standard deviation divided by the square root of the sample size. Okay? The last thing is that the shape of the sampling distribution of sample means will approach a normal distribution no matter what the shape of the population distribution is. And it will be closer to normal the larger the sample size. So let's go to the examples to see what's going on with this. All right. So let's start with a fairly simple one. If we've got movie price tickets, standard deviation for movie price tickets in the U.S. is apparently 72 cents. And our sample size that we're calculating means from is 52 theaters. So we record ticket prices for 52 theaters, calculate the mean, look at the next 52 theaters, calculate the mean. What is the standard deviation of the sample means then? Okay, so think back to our equation here. All right, we've got our population mean and we've got our, standard deviation, population standard deviation, and our sample size. So what is our standard deviation for the sampling distribution of sample means? Okay, just go ahead and unpause when you're ready to move on. All right, we've got that equation. We've got the 72-cent standard deviation and the 52 theater sample size. So that comes out to approximately 10 cents. All right, so let's look at another application. Here we've got a histogram with the population of 600 horse jockeys. Average is mean. The mean is 116.2 pounds, and the standard deviation is 3.9 pounds. As you can see, this is a left skewed distribution, so it is not a normal distribution. All right. Let's go ahead and look at the make a note of the average and standard deviation for the calculations. Okay, so here's some questions. If we use a sample size of 45, can we apply the central limit theorem? And how are the conditions met? So remember, the conditions were sample size of 30 or standard distribution. I'm going to put that silly putty away. Sometimes it just helps to keep my hands busy, but it's distracting me. Okay, next question is, what does the sampling distributions mean? And what is the sampling distribution standard deviation? And what is the shape of the sampling distribution? Okay, go ahead and answer those as you can, and then unpause and when we're ready to move on. Okay, so yes, we can apply the central limit theorem because our sample size is 45, which is greater than 30. Given that we can apply the central limit theorem, our the mean from our sample distribution of sampling means, if I've gotten the phrase right, is equal to the population mean, so it's 116.2. Okay, so for the standard deviation, we do have to use this formula for calculating it. So we've got our population standard deviation divided by the square root of our sample size. So 3.9 was the population standard deviation. We had a sample size of 45, so we get 0.58 standard deviation. All right, what is the shape then of that curve going to look like? So bear in mind, the original was left skewed, but the central limit theorem says this is going to be approximately bell-shaped. And sure enough, we have an approximately bell-shaped curve if we do that. All right, so the next one. We have starting salaries for law school graduates in 2007. We've got this really funny shaped distribution. I'm guessing these are the ones whose parents know people. Quick note, They did leave off a few salaries above 200,000, and should also note that they gave the source and properly attributed it. Okay, so what is the shape of this distribution? If we look at samples of 25, can we apply the central limit theorem? If we look at sample sizes of 50, can we apply the central limit theorem? And finally, if we use a sample size of 200, can we apply the central limit theorem? And what shape do we expect, and how would that compare to the shape we get from part C? Okay, first off, distribution is probably best classified as bimodal. As you can see here, we've got two peaks, so that's telling us we've got two highly frequent occurrences. Not quite bimodal in the same sense as we were talking about earlier in the semester, but that is usually how you describe something with two peaks, even if they're not equal size. First, in the first case, no, the central limit theorem would not apply because our sample size is only 25 and we have to have it over 30, and the population data is not normally distributed. Part C, yes, we can apply the central limit theorem because our sample size is now larger than 30. And finally, again, larger than 30, so we can apply the central limit theorem. We would expect it to start resembling a normal distribution, as we would expect for part C. And as the central limit theorem states, the larger the sample size, the more normal our sample distribution becomes. So that would be closer to a normal distribution than part C. Okay, that is it for section 7.1. Hopefully that is clear. Try not to overthink it. It's easy to, with some of the terminology, to start overthinking it. Yeah.